fixed service. There are two types of channels of frequency arrangements: interleaved plan and co-channel plan. Um, yeah, and some historical um, things need to be taken into account. For frequencies below 12 gigahertz. The compatibility of channels arrangements in the transition from analog to digital systems, if any, if some analog systems are used, but nowadays all all uh, all are digital, let's say. Yeah, and yeah, for frequencies about 12 gigahertz channel arrangement optimized for digital systems. Yeah, and yeah, about terms. So polarization. Polarization is a property of electromagnetic waves which characterizes the orientation and rotation of the electrical magnetic vector. Yeah, in here is a reference to ITU recommendation, which defines cross-polarization discrimination, cross-polarization isolation. Yeah, the link I will, these links I will paste into chat. One second. Yeah, okay. So, what is cross-polarization? This is appearance in the course of propagation of a polarization component which is orthogonal to the expected polarization. Yeah, next terms I will not read here, but yeah, but you need to go through a diagonal to see the difference. Yeah, for example, copolarization. It appearance in the course of propagation of polarization component which is identical to the expected polarization. Co, it means something I would say the same. For example, co-channel, it means in the same channel. Yeah. Okay. Yeah, maybe this cross-polarization discrimination. For radio wave transmitted with a given polarization, the ratio of the reception of the power received with the expected polarization to the power received with the orthogonal polarization. Yeah. Yeah, and what means dual polarity? Dual polarity means that an antenna can transmit and receive signals in two different directions simultaneously. This is achieved by using two sets of elements or antennas that are positioned at right angles to each other. Two sets of elements are designed to transmit and receive signals in two orthogonal planes, typically horizontal and vertical. It's classical polarizations used in radio links and other communication systems. Yeah, before we go further, yeah, please write your full name here in Zoom. Yeah, it's needed to identify you re regarding the attendance. Okay. Yeah, you can change your name in Zoom. Yeah, not needed to put your names here in chat. Yeah, it's yeah. Okay. So dual polarized antennas work by transmitting and receiving signals in two different polarizations simultaneously. Polarization refers to the orientation of the electromagnetic waves as they are propagated through space. In a single polarized antenna, the electromagnetic waves are propagated in only one polarization, either horizontal or vertical. However, in dual polarized antenna, the waves are propagated in two orthogonal polarizations, typically horizontal and vertical. Yeah, in this slide, in figures below, given example for single polarized antenna and antenna with dual polarization. Yeah, this is a technical solution for this small parabolic antenna. And to achieve this, dual polarized antenna have two sets of radiating elements, each oriented in a different polarization. These radiating elements are typically arranged in a cross-polarized configuration with one set of elements aligned horizontally and the other set aligned vertically. When transmitting, the dual polarized antenna can simultaneously emit signals in both horizontal and vertical polarizations. This allows for the transmission of two independent data streams over the same frequency band. Similarly, when receiving, the antenna can receive signals in both polarizations simultaneously, so effectively doubling the received data. Advantage of dual polarized antennas is that they can transmit and receive more data over the same frequency band, thus effectively doubling the throughput of the communication channel. This makes them highly efficient in crowded spectrums where maximizing data transmission is critical. Dual polarized antennas are commonly used in various wireless communication systems, such as point-to-point, microwave links, also cellular base station, Wi-Fi networks, satellite communication systems. They are particularly useful in scenarios where high data rates and efficient spectrum utilization are required. Yeah, and in this slide, there are some reasons which justify dual polarized antennas usage. So, as mentioned before, it increases capacity. Yeah, basically, what means capacity? Dual polarized antennas allow for more data to be transmitted at the same time, increasing the overall transmitted amount of data in the network. This is especially important at high density areas where multiple users are accessing the network simultaneously. Second is improved signal quality by transmitting and receiving data on two different polarizations. Dual polarized antennas can mitigate the effects of interference and multipass fading. This leads to improved signal quality and less packet loss, and this results in more reliable and stable connection. Third, it's better spectrum utilization. Yeah, it's a question of how effectively system uses spectrum. Yeah, basically, is we can using the same frequency transmit two data streams with the same frequency, but with different polarizations, using different polarizations. As fourth, he mentioned simplified installation. As it was shown in previous slide, dual polarized antennas can be installed in a single unit, reducing the complexity and cost of installation. This is especially advantageous in situations where space is limited or when deploying a large number of antennas. Yeah, and next is future proofing. As data demand continues to grow, dual polarized antennas provide future-proof solution by increasing capacity of the network without the need for additional infrastructure or equipment upgrades. Yeah, but it means that you need to buy such antenna. Yeah, and if you decide later, then you can use both polarizations. And for conclusion, dual polarized antennas are essential for networks that require high capacity, reliable connections, and efficient spectrum utilization. They're cost-effective and practical solution to meet the ever-increasing demand for data transmission. Yeah, plus minus 45 degrees dual polarized antenna. So this type of antenna has two radiating elements that are oriented at plus and minus 50 degrees with respect to the horizontal plane. So it transmits and receives signals with two different slant polarizations. Yeah. Typically referred to as plus minus 40 degrees. Yeah, the same applies also for mobile antennas, mobile panel antennas. They are also as basic polarization is this dual polarization plus minus 45. In fixed service, it is used in applications where polarization of the incoming signals is known and fixed, such as point-to-point radio links. Yeah, it provides better isolation between adjacent antennas and reduces the interference caused by cross polarization. It requires one feeder or connector to connect to the radio equipment. Yeah, and horizontal plus vertical dual polarity antenna is suitable for applications where polarization of signals is unknown or can vary, while plus minus dual polarized antenna is used in applications where polarization of the signals is known and fixed. Yeah, and in mobile public mobile networks, this plus minus 45 degrees slant is justified with fact that user when speak when using mobile phone, the mobile phone position is can be different positions, and very usually it is like at exactly or very close to this 45 degrees length. Yeah. Yeah. Next, so in a line of sight communication scenario where transmitting and receiving antennas have a clear, unobstructed view of each other, vertical polarization is often used. This is due to majority of man-made and natural obstacles such as buildings and trees have horizontal polarization characteristics. By using vertical polarization, the antenna can minimize the interference caused by these obstacles, and from previous lecture, you remember that horizontal polarization is more affected by droplets, yeah, by rain. Yeah, and if communication is happening in an environment with a lot of reflections, such as in a city with tall buildings, horizontal polarization may be more suitable. This is because horizontal polarization tends to have better penetration through walls and other obstacles, while vertical polarization may suffer from signal cancellation due to reflections. Yeah, with this it's said that for city environment, yeah, horizontal polarization is more preferable. Next type is circular polarization. It may be used to achieve a combination of both vertical and horizontal polarization characteristics. Circular polarization is less affected by orientation of receiving antenna, making suitable for situations where antenna may be moving or where the relative orientation between the transmitting and receiving antennas is not fixed. Yeah, and in this figure provided these typical types of polarization. We have okay, it's assuming antenna and radiated radio wave is yeah, it's visualized. Yeah. So horizontal polarization, the wave propagates in horizontal plane. In case vertical, signal propagates in vertical plane. Dual polarized example, both vertical and horizontal planes are involved. Plus minus 45 degrees polarization. Sometimes this is called just dual polarization. Yeah, but especially for in mobile communication systems, but it's yeah, it's better to say this plus minus to not yeah, we can miss it with this type of dual polarization, vertical, horizontal. Yeah, and circular polarization, there are two types. Right-hand circular polarization or left-hand circular polarization. Yeah, it's basically rotation of around this central axis when signal is propagating. So polarization of antenna refers to orientation of electromagnetic waves it emits and or receives. There are two main types of antenna polarization, as mentioned, vertical, horizontal. Polarization of antenna must match the polarization of the signal being transmitted or received for optimal performance. When polarization aligned, the signal can be efficiently transmitted or received, resulting in better signal strength and quality. If the polarization are misaligned, signal can be weakened or even completely blocked. This is because when polarizations are perpendicular to each other, the signal experiences a phenomenon called polarization loss. This loss occurs because the electric field of the signal cannot effectively couple with the antenna, leading to reduced signal strength and potentially poor communication performance. Additionally, antenna polarization also affect signal penetration and system efficiency. For example, vertical polarization is often used for ground-to-air communication because it provides better signal penetration through obstacles such as buildings or trees. But horizontal polarization is often used for point-to-point communication due to the fact it minimizes interference from other signals with different polarizations. Antenna polarization is critical consideration in system design to ensure optimal performance, signal clarity, and system efficiency. And here we continue with first type of channel arrangement. Name is interleaved channel arrangement. Basically what we have here. We have this frequency axis here on this horizontal line. Basically some starting frequency and some end frequency, or lower edge frequency and upper edge frequency. And this all we can consider as frequency band or frequency block. Usually we speak about frequency band. Next. So this 1, 2, 3, 4. These are central frequencies of radio channels. And in this quite complex solution, I use both types of polarization. We see both horizontal and vertical polarization, and for and distance between radio channels using the same polarization is given by this X. Yeah. Co-polarization channel spacing. Co, it means the same polarization. For channels with the same polarization, there is determined some constant spacing between central frequencies. And for cross-polarized channels, we see that this distance between or among between first and second channel is half half smaller. Yeah, basically x divided by 2. And here we see where this efficiency of spectrum use appears. Yeah, using different polarization channels, we can use more dense channel arrangement. Yeah, smaller this spacing is needed between channels. Yeah, and here we have basically n channels for horizontal and vertical polarization. And here in the middle we have some middle point. Let's name it middle point, which in this case splits go channels and return channels. Such definition is used in fixed communication systems to separate transmitting and receiving frequencies for FDD systems. FDD means frequency division duplex systems. Yeah, and to separate these transmitting and receiving frequencies, some guardband is needed. Yeah, and very often guardbands are used also at the lower frequency edge and at higher frequency edge. Basically, this guardband is needed to avoid or minimize the better what should be or have to be to avoid and do not make interference to adjacent radio communication systems also here and in this upper end, basically to avoid some mutual radio interference. We need also this guardband here and here. And this guardband is defined by performing EMC studies. EMC means electromagnetic compatibility studies. And those EMC or electromagnetic compatibility is achieved by making calculations, simulations, and as a result, then we achieved result. We um, we transform it in form of the size of guard band. The size of guard band for broadband systems usually are some megahertz. Yeah, even some megahertz, and this guard band actually depends how what systems is used in neighboring frequencies. Yeah, and yeah, basically what is the protection requirement. Yeah. And for different systems, this guard band will be different. Yeah. Uh, yeah, basically dual polarization, polarized systems can utilize spectrum much efficiently, as we see in this example. Next is example for co-channel arrangement. Uh, in principle, we have the same picture as before, with some little uh, some little changes. In this case, we use the same frequency for horizontal polarization and for vertical polarized signals. Here we used for each radio channel different frequency. You see frequency axis. This is F1, this is F2, this is F3, F4, and so on. But here we use for first and second radio channel the same frequency. But signals are in different polarizations, differently polarized. And such signals are called co-polarized signals. So it means, co-channel. We use the same channel or the same central frequency for these two radio channels. Here we have also one guard band here, second guard band here. This arrangement also is frequency duplex. We have one frequencies for transmitting and second frequencies for receiving. We have also guard band here in the middle part. Yeah, Yeah, one cross-polarized signal at the same frequency two adjacent channels with copolarization signals at the channel spacing delta F equals 6, and two adjacent channels here polarized signals at channel spacing delta F equal also X. Yeah, and such solution is suitable for short hops with simple modulation types. And recommendation is for frequencies about 12 gigahertz. Yeah, this is a general comment here. Yeah, and different parameters are used for characterizing quality of the transmitted data bits data. So quality and service ability indicators parameters different macro links depend on the type of network classification. These indicators are recommended by ITU-T and ITU-R recommendations, and classical parameter is BER, bit error rate ratio. And BER of 10 in order -3 is measured with time averaging equal to 1 second, and this such a value is unacceptable for most of most services. Yeah, and other value is which is used often is 10 in order -6, or in power of -6 is measured with time averaging equal to 1 minute. There are used also other parameters like this CES, severely errored seconds, or degraded minutes, or errored seconds. And there are also some other ones, yeah, but quite often is used this just bare bit error ratio in radio links calculations. Yeah, and system is considered unavailable if bare exceeds the value of this 10 -3 for 10 or more consecutive seconds. When analyzing system quality, the time period is excluded. The quality characteristics of radio links are divided into different quality groups. They are high quality, medium quality, and local quality. Typically, for radio links, the bear shall be of 10 in power minus 6, not less than 99.99% of the time per year. The high quality characteristics are applied to long radio communication links. Corresponding permissible norms are given for average and local quality parameters. Yeah, downtime or outage characteristics are divided into hardware downtime and downtime caused by radio wave propagation conditions. And amount of downtime caused by rain is usually accepted in the range of 30%. Yeah, and in this slide it's provided the reference to definitions used in the previous slide. Yeah, I will skip this slide. Yeah, sometimes they provided or used interference classification, and for point of view of propagation, interference can be classified as correlated, uncorrelated. Correlated means interfering signal propagates under the same propagation conditions as the useful signal, same phase dips for the two signals at the same time. Uncorrelated, the interfering and useful signals are subject to different propagation conditions. For worst case, the interfering signal has a maximum level. The useful signal is at the threshold level. Yeah, correlated means some for these two signals, something is common. Yeah. In this case, yeah, there is the same propagation conditions. Yeah. And from the point of view of the signal source, interference is classified as intersystem, which means internal interference. In this case, it's interference coming from the same radio site or from other radio sites in the same microwave radio system. Signal parameters are known by the system designer. It includes correlated and uncorrelated interference. Next is intersystem or external interference coming from other radio systems, sometimes only partially known by the system designer, and usually it has to be considered as uncorrelated case. quite often, uh, quite often the interference is interference source is intrasystem or internal source. Yeah, so yeah, sometimes it seems that there are some external sources of interference, but quite often, yeah, at the end, engineers conclude that the problem comes from their own radio system, and yeah, question is how we can find this the right source, which is trouble maker in this situation. Yeah, and approach is quite simple. All yeah, basically it's done by just switching off one element by element, and then engineers analyzing if interference is on the air or the interference is ended. Yeah, and yeah, and this approach is the best one and is used in practice. But in case if we, let's say, switch off all possible radio elements which could be source of interference, and interference is still on there, then it shows that real interference is somewhere outside the network, and the source of interference shall be found. Yeah, and yeah, and switched off. Yeah, in next slides, they are given interference scenario. Yeah, first is interference scenario where the same hop interference, and it regards to co-channel frequency arrangement for the same frequency, cross-polarized systems, adjacent channel, copolarized systems, and for interleaved frequency arrangement, it's adjacent to channel polarized systems. Yeah, and next slide I will skip. And yeah, there are different interference scenarios provided. Yeah, in slides this will stay, but now we will just skip this. Yeah, and okay, now we will have a 15 minutes break, and then we will continue with the next slides in this presentation. So we will now we will have break and return in 15 minutes. Okay, let's continue. So, and we'll continue about with algorithm for calculation of digital micro-link parameters. So in most cases, the calculation begins with selection of operating frequency range or frequency band. Then we need to select hardware and antenna parameters. Yeah, it's recommended to choose hardware with the smallest possible signal threshold value at the receiver input at the specified performance level, and with the ability to vary with several power level values in the receiver equipment. There are several considerations when choosing an antenna. So antennas with high antenna gain increase the energy potential of communication link signal, which improves quality indicators. Such antennas possible to reduce interference in microwave link paths due to better shielding. But high gain antennas have large dimensions as they are exposed to strong wind loads and require strong antenna support. And yeah, and basically the construction more efforts for ensuring safe construction is needed, which increase the cost of building a communication link. Therefore, a compromise between price and quality should be chosen. When choosing the location of the station and the interval of the profile, this is a very responsible design stage that greatly affects the operation of the communication link. For this purpose, high quality cartographic maps should be used. Yeah, but in most critical cases and in practice, a practical survey of the surroundings should be carried out with the highest basic marks being taken. Antenna placement heights are determined according to the criteria. After locating the stations and determining the length of the micro-link hops, the data rates applicable to each ready link hop can be calculated. At the stage of calculation of the settling reserve of the micro-link interval or hop length, timely conclusions can be made about the correct selection of the main parameters. In most cases, attenuation margin should not be less than 26-28 decibel. Under conditions with such a margin, it is still possible to meet the indicators of the requirements of the micro-link. Yeah, too large margins is economically unjustified and should be avoided. Before starting the calculation of downtime indicators, it is necessary to determine the factors that lead to malfunctions of the communication link. In considerations of frequency ranges, the operation of the link is mainly affected by rain. Link outage is unlikely at small hop lengths and is considered in some, and it's considered for some cases, taking into account all quality indicators. The value of the percentage of severely damaged seconds is determined, and the remaining values are calculated if necessary. The downtime norms and quality indicators are not met after performing the above-mentioned actions, then the calculations is performed one more time. Taking other output data for the hardware, antenna, or other parameters. Next step in calculations is the calculation of it can be taken into account also space diversity aspect. This is okay. This is more detailed calculation. But in case of non-fulfillment of norms, the signal level at receiver should be increased by transmitted power or of the radio link. This is general. These are general steps which shall be considered. Making calculations. Typical scheme in mobile communications network. Here with BTS we denote base stations. And the radio links are these arrows among each couple of BTS. And for connecting BTS with other entities of the network, we use in this solution micro-link. Micro-link is also used for connecting with central station of the network, or optical line can be used instead. And more actually optical lines are used, but micro-links are still in operation, and there are plenty of cases when micro-links cannot be substituted with optical lines. And general algorithm of microwave transmission system quality calculations with a program software yeah, basically create micro link. We we set locations for station A, station B. We set equipment, operating frequency, antenna parameters. We set calculation conditions. And do or run our simulation. Yeah, and in this slide, there are three groups of parameters. Hardware parameters, antenna parameters, and rest of parameters. Yeah. Yeah, free space loss. Okay, this topic we have already discussed in previous lectures. Okay, I will skip it. Yeah, there are list of different radio terms which are very important in radio communication, in engineering, in doing simulations, calculations, also by just choosing the right equipment. Yeah, and then again, yeah, is this expressed in this case with such a formula? Yeah, so where G is the gain over an isotropic source in decibels. K is the efficiency factor, the diameter of parabolic reflector, lambda is wavelength of the signal, and from this formula we can see that very large gains can be achieved if sufficiently large reflectors are used. However, when antenna has a very large gain, the beamwidth is also very small, and the antenna requires very careful control over its position. In professional systems, electrical steering systems are used to provide very precise positioning. Yeah, it's quite actually challenging doing this projecting in real world. Yeah, basically we can take we can plan right coordinates, yeah, but GPS system actually has some margin of accuracy, yeah, and therefore some additional systems like electrical serving systems are needed for precise positioning. of placement of the antennas. Yeah, other parameters I will not. Yeah, I will skip them. Yeah, received signal level is important, very important parameter here. The received signal level is the signal level measured at the receiver side, and it's calculated using method which we name link budget actually. Yeah, and very important parameter is fed margin. We spoke about this parameter today in this presentation. So feeding margin is difference between the sensitivity threshold for a given pair at the received signal level under normal conditions. Yeah, and feeding margin is this received signal level minus threshold value. And which should be in range of some 26, 28 decibels. Next, measurement units. Yeah, with some explanation given. Yeah, power levels, how it's calculated. Yeah, you will be able to go through these slides and yeah, read more detailed. Yeah, measurement units most often used, so dBm and decibel watts. And yeah, difference between dBm and decibel watts is yeah, 30 decibels. Here is unit conversation examples. So dBm is decibel watts plus 30. Yeah, 30 is this conversion coefficient. Yeah. If you have a value expressed in dBm, you easily can convert to decibel watts and vice versa. And these units are used very often. It's basic units, basically, in radio communication systems, especially this dBm. Yeah. So the power in dBm 0 means 1 milliwatt, or in decibel watts it's equal to minus 30. Minus 30 decibel watts. Yeah, here provided formulas and examples how to make conversion from 1 one measurement unit to other unit. Yeah, example, we have some input data and we need to calculate ERP. ERP is effective radiated power. It's a power which is measured beyond antenna, so it's radiated power. Power which is can be measured after antenna, yeah, in the air. Again, ERP we can express in dBm or in decibel watts. Difference is 30. Yeah, this coefficient is 30, and we can easily convert from dBm to decibel watts. Simple relations. Difference 30. Yeah, here there are also differently used this radiated power, which can be expressed in ERP, which means effective radiated power. An alternate parameter that measures the same thing is effective isotropic radiated power, EIRP. Yeah, the same thing, but expressed differently. And this difference comes from antenna, which we use as a reference here. dBi, it means antenna gain reference to an isotropic radiator, or other type is dBd, where antenna gain is reference to a half wave dipole. Yeah. And the difference between ERP and EIRP is actually this coefficient. Here is provided relation between both power types. Difference is 2.15. It's coefficient which relates EIRP with ERP. Yeah, it's and the source is here. We can express antenna gain in dBi or dBd. And difference is also this 2.15 coefficient. Yeah. Yeah, and basically how we can calculate radiated power of the transmitter. There's such a relation. Radiated power is equal to transmitter power minus signal losses plus antenna gain. Yeah, basically we have here radio equipment parameter, transmitter power. Here we have feeder and other elements of the system losses. These losses includes feeder loss, filter loss, and other losses. and antenna part. Antenna is characterized with antenna gain parameter here. And to calculate P, we do the same calculation, and here we use this coefficient here. Minus 2.15. Basically, so radiated power is equal to transmitter power minus all significant losses plus antenna gain. Yeah, it's general formula. Okay, signal noise figure. Yeah. Noise figure we can calculate using this very often used formula, Boltzmann constant, noise temperature multiplied by bandwidth of the device in hertz in this case. The noise factor, other parameter, noise figure. Examples about how to determine the signal status with a known radio threshold signal to noise ratio. And given an example, yeah, and this is these formulas are also important one. There are different horizons. Yeah, one is geometric horizon. Then we have electromagnetic wave horizon formula. Then we have radio horizon. Remember from previous lecture, key factor. This 1.33 value, where we take into account the spheric geometry of our Earth. Yeah. And for normal signal propagation, this key factor value is 1.33, and this value is assumed in simulations of radio links of for mobile coverage and so on. Everywhere where we apply this calculations using digital maps and Earth terrain, often we calculate as default for normal signal propagation. Yeah, it's t equal to 1.33. And optical horizon, yeah, it's worth to remember that there are such things about horizon. Geometrical, electromagnetic, radio horizon, optical horizon. Yeah, Earth's curvature, Fresnel zone, It's also basic of radio links. In Fresnel zone, the main part of signal and radiated signal energy is focused. Yeah. Yeah. Next is also like classical formula. I believe you know this formula, Shannon's formula for calculations of theoretical limit transmission channel capacity. Yeah, this one formula. Basically, C is channel capacity. Yeah, every time we speak about channel capacity and doing different using more than one polarization, we saw increased capacity of system. Yeah, basically the aim is use available resources more efficiently. And this formula talks about maximum or theoretical channel capacities. How fast is our radio link? How fast is our radio channel? Or yeah, and basically channel capacity depends of system or channel bandwidth. Basically, if we have wider bandwidth, then we basically achieve also higher data rates. For example, if we use if our mobile phone uses, for example, LTE technology with 10 megahertz, we achieve some megabits per second data rate. And if we double this LTE channel, for example, 20 megahertz, which is typical value, then using this formula, we see our final data rate will be much higher. Yeah, therefore, channel bandwidth is very important, and the same is true also for radio links. Then in this formula we see that this S over N channel signal to noise power ratio is also important, and to increase capacity we can increase this ratio. We can increase signal power, which is not economically justified, or we can improve our system and minimize noise level. Yeah. Yeah. Okay. So signal to noise ratio. Here in the table we have signal noise ratio for demodulator using 10 in power and -6 bare value. So receiver type and number of symbols, we have QM modulation and some lower modulation and higher order modulation schemes. For the proper operation of the such system, we see that for higher order modulation, we need very good signal noise ratio. Yeah, signal must be much above the noise level. So signal need to be very clear, which can be easily detected with this sensitive system. Yeah. Yeah, this is about towers where we install microwave equipment, micro antennas, the same towers which we use everywhere, often outside cities, for telecommunication towers, where we install also, of course, public mobile communications, panel antennas and other antennas, including microlink antennas. And this scheme is this scheme shows how to calculate the area needed for building such a tower. Yeah, we basically with this we can calculate the area A and B. Yeah, we can calculate area. Yeah, for yeah, for these two types of towers. Yeah, this one is a typical with 3 antenna sectors. Typical antenna type, which is used for installing mobile antennas and radio link antennas on such type of towers. Next, different terms. Different terms, basically with explanations. What is isotropic antenna, omnidirectional antenna, reflector antenna, parabolic antenna. So parabolic antenna is reflector antenna using a parabolic surface. The feeder position is in the parabola focus. So in microlinks we use this type of antennas more often. Yeah. Oh, very important also parameters, near zone and far zone. Far zone actually is area where the radio signal is formed. Basically, if we want to measure signal very close at the antenna, we can get wrong results, wrong measurement results. Yeah, depending on the size of antenna and the frequency used, this recommended distance from antenna where signal will be basically formed correctly with the right polarization is at some distance. Yeah, basically, yeah, their formula using yeah, far zone here is the formula. Basically, at this distance, signal will be formed correctly, and doing measurement from antenna at this distance, we can measure the right signal level. We will be able to distinguish the right signal polarization. Yeah, and this distance depends of antenna diameter, and operating frequency. Yeah, and D is distance from antenna to this far zone point. Yeah, far zone point basically says us that signal at this distance from antenna is completely formed. Yeah, and yeah, and here we can do the first measurement. If we need to measure signal level, we need to measure signal polarization. If we need to measure, yeah, basically signal power, radiated signal power. Other terms provided here. Yeah, okay, that's it for today's topic. So presentation is uploaded to Ortus. And yeah, do you have any questions about today's topic? If not, then we will continue in 10 minutes with the practical part for foreign students this time. So today we will have laboratory work number 5. So please download this